welcome. In this lecture, we're going to go over computer architectures. This is a lecture from a book that I wrote with Garbini and Devine on Picone. Check out the MIT Press website or the companion website for the book. All right, computer architectures, kind of an overview. Why we're interested, because we're doing real-time computing here, right? So real-time programming, this is our angle. It relies on understanding computer architecture. If you don't understand the computer architecture, it's going to be very difficult to write effective real-time programs. Okay, most real-time programs are written in C, as we've discussed, offering low-level access to memory and hardware registers. So that's part of why we use C. Okay. Computer architecture, high-level models of computer system structures, often abstracting implementation details. So we're not going to worry about some of the implementation details here. We're going to go over how the computer is structured in sort of an abstract model that's going to help us think about how it works when we're programming. It's essential for designing systems with real-time computers, as we've discussed. So here are the 5 primary components of modern computers. This is called the von Neumann architecture. It's the most common type. So here are the 5. The first 2 are aspects of the processor. So the processor control unit, the brain of the computer. So over in the figure, it's this one, the control unit. It directs the operations of the computer. The processor data path, the brawn of the computer, performs these operations and contains some of the hardware, as we'll discuss. Memory stores data and instructions. That's right here. Input receives data and instructions from the user and other devices. So that's here. And output sends data and instructions to the user or other devices. Those are the 5 primary components. So our goal is to focus on relevant ideas for real-time computing while connecting to the broader literature for deeper exploration if you want to dig in further into any of these topics. So we're going to dig a little bit deeper into the processor, memory, input, and output. So here's an overview of processors. Again, there are 2 components within the processor. The control unit, or the brain, it receives machine code instructions from memory and controls other components to execute tasks, like the memory input, output, etc. Data path, the brawn. First, registers. They're fast, small capacity memory. They're the portions of memory that we have queued up right before we're going to use that piece of data or that instruction. Buses, the communication systems within the computer. Arithmetic logic units, or ALUs, perform basic arithmetic and logic operations, as shown in this figure here. This ALU has 2 operands. We have input A and input B. And the output comes out the other side, the result. There are 2 other sides to this. So the input status and the operation code for which operation to perform, and then the output status. So input status, maybe it's good. Status is good, no errors. Output status, hopefully also good, no errors. So if this is input A, this is input B, the output depends on what the operation code is. If it's a simple operation like addition plus, then Y, the output, is going to equal the sum of the 2 inputs, A plus B. But it could be other arithmetic operations or a logic operation, for instance, as well. So the data path includes many ALUs in it. Okay, Processor architecture. Instruction set architecture, or ISA, is an abstract model describing interaction with memory, input-output, and instructions. Two examples that you may be familiar with: the x86 ISA, which is common for personal computers. So there are some manufacturers of chips based on this instruction set architecture. Remember, it's an abstract model, but you can build chips that conform to the ISA. Manufacturers of such chips include Intel and AMD, and this is the vast majority of processors historically in personal computers. ARM ISA is ubiquitous for mobile and real-time computers, gaining popularity for servers and personal computers. Manufacturers include Apple, Broadcom, and Qualcomm. So these have gained in popularity for general computing devices, but historically were more mobile and real-time computer oriented. Our MyRIO boards that we're using in this course are ARM architecture. So RISC versus CISC architectures, the reduced instruction set computing, or RISC. These are architectures with simplified instructions, fewer instructions, commonly used in real-time systems, and ARM as an example. Complex instruction set computing. So this is a more complex set of instructions, larger set of basic instructions that the processor can perform. An example would be x86 again. So those are the two paradigmatic examples of RISC and CISC. Memory. So purpose of memory is to store data, for example, numbers, files of all types, images, videos, text, etc., and instructions for the processor. Memory characteristics: speed versus capacity. The faster the memory, the lower capacity and higher cost is a pretty general rule. Volatility. There's volatile memory, which loses state when powered off. Okay, so if it loses power, you lose whatever was in memory. And then there's non-volatile memory, which retains state without power, which in some instances is very important. And then optimization. Frequently accessed data and instructions are moved to faster, smaller, and more expensive memory. That's also a general operating principle with memory. We want the parts of the data that and the instructions that are used frequently or used soon to be in faster memory. Memory hierarchy. So taking a look at the figure, it's a nice pyramid. The higher levels, for example, the register or the cache, are faster access, smaller capacity. So as you go up, you get to faster and smaller. And at lower levels, hard drives, slower access and larger capacity. So main memory, secondary memory. So main memory is where the program that's running is usually living. So the instructions are in main memory. Usually, much of its data is also in main memory. Occasionally, you need too much memory for it to all live in main memory, and you have to go to secondary memory. As the instructions are getting queued up, they might go to cache or to the register eventually right before they're executed. Okay. Memory representation and organization. So binary representation. Memory is a collection of bistable devices that represent binary digits or bits. Binary digits are 0 and 1. Okay, so a bistable device can represent two states, so we usually give the two states the names 0 and 1. Organization. 1 byte is equal to 8 bits. So there are 2 to the 8, 2 for each bit. To the 8 equals 256 unique combinations of bytes. A nibble is half a byte. So 4 bits in a nibble. And, it's cute, right? Because a byte, a nibble. Addresses in memory. Each byte has a unique address. Addressing enables identification and manipulation of memory locations. Okay, so if you need a piece of data from memory, you need to know where to get that piece of data, and that's what the address is. C programming advantage provides low-level access to memory addresses, which can be essential for real-time programming, as we'll see. Okay, finally, input and output. Input, output. We usually use I/O for this. Inputs, signals representing data from external devices, which can be from the user, like keyboards, but it could also be from other devices like sensors or remotely communicated commands from a user or from another computer. Outputs, signals representing data sent to external devices. For example, a display for a user, printers, we're all familiar, actuators like motors. So that's something that we'll do in real-time computing, is output to an actuator. Processor data path handles input-output by storing input data in memory, using input data in programs, and transferring data from memory to output devices. So we've got that processor data path that's handling the I/O for us. Real-time applications, it's crucial to understand how I/O communicates with external devices, and we're going to explore this extensively in Chapter 3 when we talk about communication protocols and the different types of inputs and outputs, digital, analog, etc. Focus in Chapters 1 through 3 is the programming of the target computer for the user interface. The input for the user interface is the keypad. The output is the LCD, the display that we're going to program to show the user different pieces of data and to interact with the user. Future chapters, we're going to be programming I/O to interact with sensors and actuators. So it's not just going to be UI, it's also going to be sensors and actuators in these later chapters. So something to look forward to. All right, we'll see you in the next section, 1.2.